Cool. So today we are very lucky to have Luca Iliesiu. I hope I did not butcher your
That was
last name.
great. That was great.
Cool. Presenting. So he just graduated. He just got his PhD at Princeton. Now he's a postdoc at Stanford. And so he'll be talking about the statistical mechanics of near-extremal black holes.
Awesome. Thanks so much for the invitation again. Yeah, as Ashton mentioned, I'll be talking about the statistical mechanics of near-extremal black holes. So please, since this is a smaller seminar, please interrupt me as much as possible with as many questions. So this work that I'll be presenting is based on these two papers. This one is with Joaquin, who I think is in the audience. And the later work that I'll be presenting is in collaboration with Matt Heidemann, a postdoc at Princeton, Iliesiu, who's a grad student, and Joaquin again. That should appear very soon, sometimes in the next couple of weeks. Okay, so I want to start my talk by reminding you of an old puzzle that occurs in black hole thermodynamics, and more specifically, when looking at the thermodynamics of near-extremal black holes. So black holes with extremely low temperature. So the puzzle goes as follows. So suppose that we want to compute the energy of some near-extremal black hole above extremality. So suppose that we fix, let's say we look at Reiser-Nordstrom or even Kerr, and we fix the charge of the black hole or angular momentum. We take the extremal state, which has 0 temperature, and start raising the temperature a little bit. How does the energy scale with the temperature in this system where the charge is fixed? So this calculation is very easy to do. The only thing you need to do is take the Einstein-Maxwell action, or whatever action, whatever gravitational theory you're studying, and just plug in. So let's say we take Einstein-Maxwell and plug in your near-extremal solution. And you'll find several terms. One term that will give you a contribution to the entropy, another term that will give you a contribution of the contribution of the ground state. I think it comes with a plus. And finally, you'll also get a term that gives you the contribution that shows how near-extremal black holes scale with temperature. And this answer will look something like minus some scale, which I'll mention in a second what it is, divided by beta. So this is a general feature. If you plug in near-extremal solutions into your favorite gravitational action, this is the result you'll typically get. So, this gives us what the free energy of the theory is in a semi-classical level. And with this free energy, we can easily obtain, the energy of such black holes. The energy of such black holes, if you look at a free energy that scales like 1 over beta, the energy would scale like t squared. So this is how the near-extremal black hole energy scales with the temperature. So the puzzle that brings up is the following. Suppose that such a near-extremal black hole radiates a single Hawking quanta. So in a semi-classical calculation, we can estimate the energy of a single Hawking quanta to be proportional with the temperature of the black hole. So here I plot the energy of a single Hawking quanta, and here I still plot the energy of the near-extremal black holes. So the puzzle is the following. Suppose I am at a low enough temperature that I'm in this area. Then what happens? So if a black hole tries to radiate even a single Hawking quanta, then it will either lower its energy down to extremality, or it will completely change its temperature by order 1%. So by radiating a single unit, a single quanta, you completely alter the temperature of the black hole. So that means the thermodynamic approximation in the system fails. There's a thermodynamic breakdown of near-extremal black holes at small temperatures. And this thermodynamic breakdown was famously brought up in this paper by Preskill and collaborators. And over time, there have been several proposals of how to resolve this breakdown. And I want to bring some of them up. Oh, and very importantly, the scale at which these two lines intersect is simply given by some of the parameters of the black hole, and is I'll motivate why it's typically referred to as E gap in 1 second. So just to give you some sense of the parameters involved. If I look at a 4D black hole in flat space, so this is just the regular Reinstein-Nordström that you have in every GR book, then the energy of such black holes scales in exactly the way I told you. And this parameter E gap is given by the ratio between R0, the extremal radius of the horizon, divided by L Planck squared. So this is, maybe the better way to write it is R0 times R0 over L Planck squared. So this is an extremely large number. But in any case, we're in a regime where the semi-classical approximation for the black hole should, in principle, still be stressed. And what I mean by that is that we're at a scale where the black hole can be arbitrary. We're concerned with effects for arbitrarily large black holes. So these are not black holes that are comparable to the string scale or something like that. So we shouldn't expect stringy effects to come in and correct this result in any important fashion necessarily. So the question is, what's happening? How is this thermodynamic puzzle resolved? So just to rephrase the thermodynamic puzzle, what we're actually interested in is how the density of states behaves at small energies, because that will obviously give the low temperature behavior of E as a function of tau. So this is given by, at low temperatures, it's given by what happens in the density of states in this region. Yeah, the thing that we will want to compute in this talk is rho of E at scales compared to E gap. And there have been various proposals coming from string theory. So for instance, there's a famous D-brane construction from the 90s in the D1, D5 system made by Maldacena and Susskind, which proposes that the way to resolve the puzzle is that E gap should literally be interpreted as a gap in the spectrum of the energies of black holes. So in other words, they propose that extremal black holes have some ground state degeneracy given by e to the s0. Then there's no near-extremal black holes in this energy sector. And then the near-extremal spectrum starts at some point. So that's one result. A similar result was obtained in some sense in a more universal fashion by Maldacena and Strominger, by using certain properties of superalgebras and 2D CFTs. We can ask, is this result universal? Is the existence of a gap universal for near-extremal black holes? Or is it actually specific to the models that they study, which have a lot of supersymmetry, so are not the most generic near-extremal black holes that are interested in, for instance, the ones in our own universe that are Kerr black holes. Specifically in this talk, I'll discuss whether or not their results apply to Reinstein-Nordström and Kerr-Newman black holes. And I just want to point out that this puzzle is related to another very important puzzle, which is about the ground state degeneracy of the extremal state. So suppose that we don't have supersymmetry. Then the semi-classical computation would suggest that e to the S0 should literally be interpreted as the ground state of the extremal state. But in the absence of supersymmetry, what protects this degeneracy? So just to get a sense of scale for what this degeneracy means, if we take a Reinster-Nordstrom black hole that has the mass of our own sun, for example, this degeneracy e to the S0 would be 10 to the 10 to the 76. So it's an absolutely massive degeneracy that, from a quantum mechanical perspective, there's no symmetry that protects it. So there's no real expectation that it should actually be there. So does e to the S0 actually measure the ground state degeneracy of extremal black holes? And I'll resolve this for Reinster-Nordstrom and for black holes and supergravity within this talk. So in order to take an unbiased view, because the results in the papers mentioned before were mostly conjectural, I'll rename E-gap as ESL2, and I'll make it clear why I'll call it ESL2 towards the end of the talk. But I just don't want you guys to confuse the fact that there should necessarily be a gap in the spectrum if I call E-gap E-gap. Any questions so far about the motivation? Okay. So the complete computation that we want to do is we want to reliably compute the partition function and density of states in Reinster-Nordstrom black holes in the canonical and grand canonical ensembles. And we'll start by first doing that in Einstein-Maxwell theory. And then if I'll have time, I'll explain how to do it in 4D n=2 ungauged supergravity in order to actually compare with the conjecture by Juan and collaborators that he made in the 90s in string theory and see if supersymmetry brings in something special. And the tool that we'll be using is, we'll be using the fact that in the near horizon region, we can approximate the gravitational theory as a theory of dilaton gravity coupled to gauge fields and matter fields. And I want to say that this idea has come up in a ton of past works, but an important distinction between past works and our works is that most of the past works which were concerned with understanding the relation of near-extremal black holes to dilaton gravity didn't necessarily want to understand such low temperature corrections that we'll be interested in this talk. They were more interested in understanding, the comparison of like the classical behavior and what consequences it has, what consequences the fact that the near horizon region is well approximated by JT gravity. But I do want to bring up this work by Almeri and Kang from 2016, which indeed identified correctly what the role of this E-gap or ESL2 plays. And I'll mention that later in the talk. So the important tool that we'll be using here is the fact that near-extremal black holes in the classical behavior, the classical solutions for near-extremal black holes always look like the following. And as we go close to the near horizon region, the space factorizes into a space that always looks like ADS2. Times some manifold. And in this case, 4-dimensional Reinster-Nordstrom black holes, just to be concrete, that manifold will just be a sphere. But I'll explain that this can be something more complicated. So I'll be mostly focusing in this talk on 4D, but I'll make some comments towards the end about 3D. And I just want you to keep in mind that most of the results that I'll present today applies to black holes, near-extremal black holes across various dimensions, both in ADS and in flat space. But I'll focus on the case of flat space.
Question? So do your results, the actual calculations that you do they also apply to the rotating black hole?
Yeah, to some extent. So here I'll be discussing today, I'll actually be discussing Kerr-Newman black holes, so black holes that have both charge and angular momentum, for which the angular momentum is sufficiently small. But in principle, our techniques could be also extended to apply to Kerr black holes. The reason why I don't do this in this paper is because in that case, the space doesn't quite factorize directly into ADS2 times some internal manifold. There's some twist as you go closer to the horizon. There's some twist in the S2 direction. But I'll explain why specifically this works for Kerr-Newman black holes with low angular momentum, if I have time.
In that case, you have this nice factorization property.
Yeah, you could say that you do that. If you have low angular momentum, you do. It's not quite like that, and I'll explain why in the region in a second.
Thank you.
Okay. I'll start by explaining, reviewing a little bit of the dynamics of near-extremal Reinster-Nordstrom black holes from a slightly different perspective than what people usually do in GR books. As you all know, the Reinster-Nordstrom black holes are solutions to the Einstein-Maxwell action that includes a curvature term, a cosmological term, cosmological constant term, and the Maxwell term. The technique that we'll be doing today is that we'll make an ansatz for, in the case of a spherically symmetric space, we'll make the ansatz that the metric could be factorized into some 2D metric and some S2 internal space, where the size of the S2 internal space is captured by some dilaton field, chi. And I put this unit of chi to the power 1/2. G mu nu can be anything in here. I didn't plug in any solution yet, but I put this factor of chi to the 1/2 in order to get rid of the kinetic term that will be generated by chi. In order to keep dimensions, chi has dimensions of length squared because it's an area. And in order to have something dimensionless, I just put this ratio where R0 will serve as the extremal horizon size. So I just rescale chi by R0. Good, but this metric ansatz is not the most general metric ansatz that you could make. In principle, you should also care about the fact that in the gravitational theory, you have some diffeomorphisms that could change your location along the S2. So in order to capture that, we have to introduce an SO free gauge field that couples to the killing vectors of the sphere S2. So with this metric ansatz, we can just plug this in to our action, and we'll find the following. So we'll find that by plugging in this metric ansatz, the Einstein-Maxwell action reduces to a theory of 2D dilaton gravity that has some potential U of chi, but quite importantly, it has no kinetic term for chi. That's achieved through this power of chi to the 1/2. It just so happens. The second term is a gauge field that captures the SO free isometry along the S2. So this is like an SU2 Yang-Mills term in 2 dimensions. The third term is the reduction of just your Maxwell field from 4 dimensions down to 2 dimensions. So it just gives you a 2-dimensional Maxwell term. And finally, there's a term that captures the contribution of all the other Kaluza-Klein modes that I didn't already capture. And it just so happens that in this case, all the other Kaluza-Klein modes are massive. So here in these 3 terms, I capture the contribution to the 2D action of all the massless Kaluza-Klein modes, namely, symmetric, the S wave of the metric, the SO free gauge field, and the S wave of the field strength. But you can put all the massive Kaluza-Klein modes in a separate term, and the reason why I do that is because in the near horizon region, the masses of the Kaluza-Klein modes will scale like 1 over the radius of the horizon. And in the regime that we're interested in, namely the near-extremal regime, the temperature is much smaller than the scale of 1 over R0. So it turns out that one can do a rigorous computation and prove that these Kaluza-Klein modes don't affect the density of states at the level of accuracy that we're interested in, namely at energy levels that are comparable to the E-gap scale or ESL2 scale that I mentioned before. But if you're interested, I can mention more about these Kaluza-Klein modes after the talk. But for now, let's just ignore them. So what can we do? Well, one thing that is nice in 2 dimensions is that in principle, we can integrate out our gauge fields exactly if we neglect the contribution of the very massive Kaluza-Klein modes. So that's because in 2 dimensions, gauge theories have a property, which is that they are invariant under area-preserving diffeomorphisms. So in principle, I could take my manifold and just attempt to do the integral over dA and dB, exactly. And using this property of invariance under area-preserving diffeomorphisms, you can completely integrate them out and rewrite your partition function as a sum over charges and over SO3 or SU2 representations, depending on whether you allow fermionic degrees of freedom or not. This is just the dimension of the SU2 representation, so it gives you the degeneracy of each state that has a certain spin. J here, it should be interpreted as the spin of the black hole, actually. This is just the character of SU2, and mu SO3 is the chemical potential that we can impose at infinity for black holes that are rotating. Then we can include a chemical potential for the charge of the black hole for the U1. So this is the chemical potential term that you see. And essentially the contribution of the gauge field gets completely replaced by some term that depends on the dilaton and on the specific charges of the black hole and on the specific angular momentum of the black hole. So before we had a theory of dilaton gravity coupled to a gauge theory, and now by integrating out the gauge theory, I just obtained a theory of dilaton gravity, but this time with a more complicated potential of chi, because I now generated these terms that depend on chi. So this is an effective theory in each charge and spin sector. So this is the grand canonical ensemble for the black hole. And one can take this action, this new action that explicitly depends on charges and angular momentum, and actually solve the equations of motion. And what one finds is kind of funny is that, for instance, if we solve the equations of motion for j equals 0, we'll find that the dilaton has some profile, and the 2D metric that is part of the 4D ansatz that was left general also has a profile, which precisely matches the Reinster-Nordstrom solution that you typically find in GR books. So even though we integrated out these gauge fields, you still see the fact that the classical solution in the resulting dilaton gravity is also precisely gives you the Reinster-Nordstrom solution. And it turns out that if you turn on J, instead of finding Reinster-Nordstrom solutions, you find small deformations, which are called Kerr-Newman solutions. And actually, one thing that we learned in this project is that if a funny way of writing the Kerr-Newman metric is actually the following. You can rewrite the Kerr-Newman metric in the following form, where your SO3 gauge field are turned on to a non-trivial profile that breaks the SO3 isometry of the sphere down to a U1. So essentially, you could say that the Kerr-Newman solution is exactly like the Reister-Nordstrom solution, but you have some non-trivial profile for the SO3 gauge field. Good. But from now on, to simplify the discussion in this part of the talk that's non-supersymmetric, I'll focus on the canonical ensemble which J equals 0, but macro-canonical in Q. So I still sum over all U1 charges, but I fixed the SU2 charge to be J equals 0. So now we integrated out the gauge fields, but we still have to understand the remaining path integral. Oh, sorry. Which is over the dilaton and the metric. So in order to do that, we'll go to the near-extremal limit, where classically, at least, the space factorizes as ADS2 times S2. So our intermediate goal will be to go beyond the semi-classical limit in which we just like solve for this near horizon action and find the on-shell solution and plug it back into the action to obtain the free energy. But we actually want to perform the path integral in the near horizon region accurately. But this brings up some problems. So the problem is that if I actually wanted to integrate out the dilaton and metric, I can do it fairly easily in the near horizon region. The reason why is in that regime, the potential can be approximated to be linear. But it's very hard to do it in the far away region, in the region far away to the horizon, where the boundary is asymptotic, where the space looks like R3 times S1 as you go closer and closer to the boundary. And the reason why that is that the dilaton action is very nonlinear, and the KK modes that were massive that I mentioned previously are actually very light here. Because as I go closer and closer to the boundary, the internal dimension of S2 becomes larger and larger. So I actually can't neglect the KK modes. So in order to resolve this problem, I do the following trick. I can separate my space into two parts. A part that's arbitrarily chosen that I call the near horizon region, and a part that's arbitrarily chosen that I call the far away region. The way in which you separate them is by some curve that I draw here in blue, on which we just impose Dirichlet boundary conditions. So I cannot specify the location of the curve in the diffeomorphism invariant way, but I can specify, diffeomorphism for invariant quantities, like saying that I want the curve to have a fixed proper length, L, and the fixed value of the dilaton, phi equal phi b, let's say. So this curve can be anywhere in as long as these two properties are satisfied. And then what I can do is I can take my metric in the faraway region and expand it around not the near extremal solution, but the extremal solution, and include some variation, delta G mu nu. And it turns out that if you take this metric and plug it in your action and expand in delta G mu nu, you can actually find that to leading order, the contribution of delta G mu nu is given by a total derivative in the action. And the lucky thing is that we can integrate that total derivative by parts. And essentially what that leads to is it leads to boundary terms, one that is placed at asymptotic infinity, that won't have much of an effect because we fix boundary conditions at asymptotic infinity anyway. And the other that is placed along this blue line, for which I chose these Dirichlet boundary conditions for the metric and the dilaton. And it turns out that the contribution of after integrating by parts, the contribution of this of integrating this by parts leads to a boundary term that's precisely the Gibbons-Hawking-York term for the action in the near horizon area. So essentially, I've expanded my metric in the faraway region around its extremal value, and I still allow the near horizon area to have whatever metric it wants. So this means that this space has some sort of discontinuity in it. Here we fix the metric, and here we let it and here on the left we let it fluctuate. So what this means is that there's some difference between the extrinsic curvature of this curve measured with respect to the normal vector pointing to the right, and the extrinsic curvature of this curve measured with respect to the normal vector pointing to the left. And this difference will precisely yield the Gibbons-Hawking-York term that we're used to when we study a theory of dilaton gravity like JT gravity. So now that I told you what to do with the faraway region, the thing that remains to do is first we can actually evaluate what the contribution of the faraway region in the action is at the classical level. This simply gives us beta times m0. So this just gives us the term that you saw in the action earlier that gives you the ground state energy of the extremal black hole. Now, in the near horizon region, as I previously alluded to, I have the option of expanding my dilaton field chi into its value at the horizon, so its value here, which I'll call phi 0, and fluctuations around that value, which I'll call phi. So now the question is, in terms of phi 0 and phi, what is this near horizon action, and how does one quantize it? This near horizon action ends up having two terms. The first term is very simple. It's the only term that depends on phi 0. It includes a bulk term and the boundary term. But in 2D, the sum between such a bulk term and boundary term is topological. It just gives you the Euler characteristic of the manifold. And since we're studying disks, the Euler characteristic of the manifold just gives us 2 pi, a factor of 2 pi. So overall, the contribution of the first term just gives us a factor of 2 pi times R0 squared divided by G Newton, which precisely matches the black hole entropy of the black hole. Sorry, the black hole entropy. That's what it should have happened, because this is the only place where phi 0 comes in. So this is the only place where the extremal radius comes in. And we know that the black hole entropy depends on the extremal radius. And the second term that we obtain in the near horizon region comes from the fluctuating piece of the dilaton, so from phi. And once again includes a bulk term and the Gibbons-Hawking-York term that was generated by integrating fluctuations in the faraway region by parts. And the only thing that phi does in the bulk is that it imposes that R plus the 2D cosmological constant. This 2D cosmological constant is actually obtained as a function of Q and J. The U1 and SU2 representations. So it just imposes this. So if I integrate out phi, I completely get rid of the bulk term. So all the degrees of freedom are captured in this Gibbons-Hawking-York term that is present at the boundary, this kind of artificial boundary where I glue the near horizon region to the faraway region. The thing that I can do is, for instance, I can choose Poincare coordinates for the ADS2 region, because now I know that phi imposes that the space is, the integrating out phi imposes that the space is ADS2 even at a quantum level. So we can write ds squared as dz squared plus d tau squared divided by z squared. And if I impose that the metric, the boundary metric is fixed, so if I separate the faraway region and the near horizon region by this Dirichlet-Bering, if you want, So if I impose that it's fixed, I can just solve for z as a function of tau, plug it into this extrinsic curvature, and the resulting thing that we'll find is we'll find that this difference of the extrinsic curvature -1 can just be replaced by the Schwarzian derivative with respect to this coordinate tau, with respect to a boundary parametrization time u. So here u is chosen arbitrarily in such a way that GUU is a constant. And the important fact here is that the constant value of the dilaton appears, this phi b of q. And it just turns out that, for instance, for black holes in flat space, this boundary value of the dilaton that separates the near horizon region and the far away region can actually be rewritten in terms of the ESL2 scale that I mentioned earlier in the talk. So this is how ESL2 appears in my computation. It appears through the boundary value of the dilaton that separates the two regions. So for instance, for black holes in flat space, this just gives a factor of q cubed divided and multiplied by O Planck.
So the boundary term's invariant for where you pick the boundary?
Sorry?
The boundary term is independent of where you pick the boundary, is what you're saying?
Yes, so I'm not allowed in gravity to specify the exact location of the boundary. Like I cannot do that in a diffeomorphism invariant fashion, right? I have to only specify, in principle, I should only fix diffeomorphism invariant quantities. And what I fix is the proper length of the boundary and the value of the dilaton. So in principle, because the near horizon region has, you know, like the metric is fluctuating. Well, it's fixed to ADS2, but the exact location of the boundary is fluctuating. I don't actually specify where the boundary is.
I see.
But if I look at the outside region and look at what the solution for phi is for the dilaton, and look at where phi and look at where the blue curve has proper length, some proper length L, then I'll actually find that this value of the dilaton is precisely related to the parameter ESL2 that I mentioned in the beginning of the talk.
All right, thank you.
Of course. Okay. So now the question is, what does this mean? The fact that the Schwarzian is multiplied by a factor of 1 over ESL2. In what regime is in what regime are quantum effects important in this theory? Well, in order to see that, I can make the following rescaling. If I rescaling in this Schwarzian action U by AU, then I can see that the action is invariant as long as I rescale beta by beta over A and phi by phi over A. So this simple rescaling suggests that the Schwarzian action is not does not depend arbitrarily on phi and beta, but rather the partition function only depends on the ratio between phi and beta. So this ratio can be rewritten, as I mentioned previously, as T over ESL2. So this can be viewed as the effective coupling of the Schwarzian theory. So in what regime is the system strongly coupled, and in what regime is the system weakly coupled? So the system is weakly coupled when T over ESL2 is much larger than 1. In that regime, I can completely trust the saddle point approximation for the Schwarzian theory. So this is actually the classical regime, and this is the regime in which most people talk about when they look at near-extremal black holes. So this is when the temperature is much larger than the gap what people conjecture to be the energy gap. So this is not that interesting, and we don't really care that much about it because we're precisely want to determine the density of states in the regime where T is of the same order as ESL2. So in that regime, the theory becomes strongly coupled. And what that means is that instead of having the boundary curve at some fixed location in ADS2, or rather at some fixed extrinsic curvature K, now the boundary curve is actually allowed to fluctuate. So I have to sum over all possible geometries in which the boundary curve fluctuates, and there's no one dominating geometry. And this fact that ESL2 is that the gap scale is the previously conjectured gap scale is the scale at which this mode becomes strongly coupled, was previously identified by Almery and Kang in 2016. But here we'll go further and actually show that one can still perform the path integral, even in the presence of the gauge fields and Kaluza-Klein modes and so on and so forth. So now, I won't discuss the quantization of the Schwarzian theory, which is the last step in order to obtain the final results. I won't discuss that in detail, but I'll just mention that it can be obtained from localization, from a dimensional reduction of Liouville theory, from SL2RBF theory, particle magnetic fields. There's tons of ways to obtain it. But the important result is that it can be written as not a sum, but an integral over energies, where the density of states is given by a sinh of square root of E. And the final result is this one loop factor multiplied by this exponential. And I just want to remind you that at the beginning of the talk, I actually wrote what the typical action is when people look at Reinster-Nordstrom black holes, how it depends on beta. And I wrote down that there's a term that, I wrote down that there's a term that looks like 1 over beta. And this is precisely this term that I find in this exponential. But very importantly, it's corrected by this one loop factor, which has a large effect when the ratio between phi b and beta is order 1. So that's the ratio in which, that's the regime in which the temperature is proportional to the gap scale. Good. So now I have all the ingredients and I can put everything together. I can take the previous result that I had for the contribution of the action from the faraway region. This is just given by this term that yields the ground state energy. Then I have the chemical potential that appeared when I integrated out the U1 gauge field. So this chemical potential was associated to the holonomy of the U1 gauge field around the S1 at infinity. Then I have an entropy term that came from the topological term in JT gravity. And finally, I have this result that comes from the Schwarzian that actually exhibits no gap, right? Here, I wrote things as an integral over dE. So if I plot rho of E, there's no space for a gap. It's not a sum over some delta functions. And I'll contrast that with a result in supergravity that I'll obtain in a few minutes. Okay, so for the spectrum of masses, we have a winner. If I look at the spectrum of masses, of black hole masses, as a function of Q and L, in principle, I see no gap. I see like a continuum. But here we can kind of extrapolate up to what scale, like we know that the spectrum should actually not be a continuum if we think that black hole microstates exist. So there should be some corrections to our results. And we can look at the scales at which the corrections, like the things that we neglected, like the massive Kaluza-Klein modes, or this potential in JT gravity, we can look at the scale at which that comes in. And it comes in at a 1 over S0 scale compared to E gap. So essentially, we can guarantee that the gap between the extremal and the near-extremal state in Reinster-Nordstrom is not at the scale that people call DSL2, but it's rather at the scale that people would call, at the scale of ESL2 divided by S0. At least that scale, maybe even lower, maybe even ESL2 times e to the minus S0. But this is rigorous and this is speculative. But for instance, if I look at a completion of this model given by something like SYK, the actual gap that people see there actually scales like e to the minus s0, but we cannot be entirely sure. Nevertheless, this tells us something very important. It also tells us that, for instance, if we take this result or this result at face value, it tells us that S0 actually does not count, e to the S0, does not count the ground state degeneracy of the Rhinestone-Nordstrom extremal black holes. Rather, it counts if I look within some energy interval given by this ESL2. E to the S0 is just the number of states contained within this interval. But for instance, if I trust that, trust something like an SYK completion, and say that the gap is ESL2 times e to the minus S0, then the ground state degeneracy of the near-extremal black hole is order 1, as one should expect from the fact that we don't have any symmetry that protects this ground state. But even if I don't trust that, and I only believe that maybe there's a gap at the scale ESL2 over S0, then the ground state is so much lower. The ground state degeneracy is so much lower than the naive Bekenstein-Hawking estimate. Okay. So a couple more things. Yeah, it's just a disclaimer. So here, because we didn't account for everything, like we have all these Kaluza-Klein modes, which in principle, they're not renormalizable if we account for all of them. We're not counting microstates in this in this way of computing the partition function. We're just giving a accurate estimate of what happens with the partition function at certain energy scales. So we're only probing things at the value of the gap in the density of states. Good. So I just want to quickly revisit the old puzzle. So in the old puzzle, we saw that the energy of the black hole at low temperatures was always lower than the energy of one Hawking quanta if I go at a temperature scale below ESL2. Now, what happens is that I see that there's, if I compute the energy again, I see that there's a quantum correction that came from the one loop determinant associated to the Schwarzian. And this is this free halves times t. So essentially, quantum corrections cure this paradox. Namely, the energy of the black hole, of the Rhinestone-Nordstrom black holes, is always higher than the energy of the Hawking quanta that such black holes can emit. But still, at low energies, there's still a breakdown of thermodynamics that's explained by the fact that the quantum theory becomes strongly coupled. Good. And I also just want to mention, because I'll talk about supersymmetry in the next 10 minutes, I also want to mention that in the non-supersymmetry case that I just exhibited, there is a gap between the lowest extremal state and the lowest extremal state with J turned on. So here, within the J equals 0 sector, there's no gap. This looks like a complete continuum. But if I want to change spin by, let's say, 1 unit, so I want to set J to 1/2, the difference between this ground state energy and this ground state energy will be given by this factor. And this factor will be important in the supersymmetric, or not quite this factor, but a similar factor will be important in the supersymmetric theory. So let me just skip this for time-related reasons. So now I want to mention a related direction, which I've alluded to throughout this entire talk. So I asked at the beginning of the talk whether supersymmetry brings in something special. Does supersymmetry actually have a gap between the extremal and near-extremal states? So in supersymmetry, there are special states called VPS states, and I'll explain what they are in a second. And we can consider excitations above the VPS state. So those are the analog of near-extremal states in the context of supergravity. So here we will consider a setup of 4D n equal to supergravity, which was considered actually by various authors and various string theory constructions, like it's related to the construction by Malthusson and Seskin, and it's also related to the entropy counting of Strominger and Vafa. The question that we'll want to ask is, how does one compute the partition function for such black holes in supergravity? And does one see a major difference from the non-supersymmetric case? The extremal solutions have 0 temperatures and preserve half of the supersymmetry in 4D n equal to supergravity, and are therefore called half BPS solutions. And the question is, can we describe the near BPS spectrum? So I just want to outline the similarities and differences. I won't go through all the analysis all over again, because I'm pretty close to being out of time. And I just want to point out the similarities and differences compared to the non-supersymmetric case. So in the non-supersymmetric case, it was actually very important that the space factorized into an ADS2 times an S2 in the near horizon region. And the isometry of this space was SL2R times SU2. And that actually was ended up being an internal symmetry of the Schwarzian theory, the SL2R. Now, in the case of near-extremal black holes and supergravity, it turns out that the near horizon isometry is a supersymmetric extension of this theory. It's a supersymmetric extension with 8 supercharges, which is PSU112 times SU2. So PSU112 is just a supergroup that's usually associated with one-dimensional superconformal field theories, just like SL2R is associated with the conformal is the conformal group in one dimension. Good. Now the problem is that if I redo, the entire apparatus of separating my space into a faraway region and a near horizon region, the action that I end up getting in the near horizon region is n equal 4 super JT gravity. And that ends up reducing again to solely a boundary term in a much more complicated way, but let's leave the details aside. But the theory that I end up with is the n equal 4 super Schwarzian theory. Now, unfortunately, people have not studied this theory that much. There has been some debate about the action of the n equal 4 super Schwarzian theory itself, not to even mention its quantization. But luckily, we were able to obtain the n equal 4 super Schwarzian action by constraining the space of n equal 4 super diffeomorphisms. And we obtained an action that actually contains 10,000 terms if you expand in components. But luckily, the techniques that were used to quantize the Schwarzian theory, which was the localization technique, only relies on the quadratic terms in the action. So if you expand around the saddle point of the action, you only need to keep the quadratic terms in order to fully capture the quantization of the theory. So this provides us with a great simplification coming from the fact that the integration space associated to the n equal 4 super Schwarzian also allows for the same localization technique to be used. Just to be more precise, it comes from the fact that the integration space for our variables it ends up being the space of super diffeomorphisms that has to be quotiented by this PSU112 group in order to get rid of the 0 modes associated to this action. It ends up that this integration space is symplectic and therefore allows for the use of some localization techniques for the path integral. So I won't go into details, I'll just mention what the bosonic part of this action is, because that's very simple and it's very simple to understand where it comes from. So PSU112 has an SL2R times SU2 subgroup, and the SU2 is an R symmetry of the theory. And it actually corresponds to the black hole angular momentum. So in the same way that we had an SU2 gauge field previously that captured the black hole angular momentum, this time this comes from an SU2 R symmetry gauge field in 2 dimensions. So if I actually look at the effective boundary theory that this SU2R results in, it results in a particle moving on an SU2 on an SU2 manifold. Sorry, this would be actually SU2 because now I'm allowing fermions. So this is the action of a particle moving on SU2 coupled to the Schwarzian. And supersymmetry actually imposes that the coupling, this ESL2, precisely matches the coupling of the SU2 of the particle moving on the SU2 manifold. So the schematic result obtained from localization is that I can take the on-shell solution just for the bosonic components, because I know that the on-shell solution for the fermionic components is just that all fermionic components are turned off. I can just take the possible on-shell solutions. Now, the possible on-shell solutions are labeled by an integer, n, that you could think about as giving rise to SU2, counting SU2 instantons in the 2D bulk. So I can write my overall partition function as a sum over SU2 instantons times e to the I on-shell, the on-shell action, multiplied by the one-loop determinant coming from each field, the contribution of each field. So there's a one-loop determinant coming from the fermions, a one-loop determinant coming from the Schwarzian field, and a one-loop determinant coming from the particle moving on the SU2 manifold. And you can compute each of them. And the important thing that I want you to notice is the scaling with beta of these terms, because the scaling with beta just counts the number of zero modes associated to each degree of freedom. So for instance, let's start with the Schwarzian and the SU2. Notice that they both have beta 1 over beta to the power 3/2. And that's because there's a 1 over beta to the power 1/2 associated to each bosonic zero mode. And the Schwarzian has free zero modes associated to the free generators of its SL2R symmetry. In a similar way, the particle moving on a group manifold has free zero modes associated to the free generators of its SU2 symmetry. Now, as I mentioned previously, there are 8 total generators of PSU112 that are fermionic. And each fermionic zero mode comes with an opposite power compared to the bosonic part. So it should come with b to the 1/2 for fermionic. This was bosonic. So the power that I expect is if I have 8 fermionic zero modes would be beta to the 4th, which is precisely the power that I find in the one loop determinant of the fermions. So now I can put everything together. And miraculously, you can actually end up doing this sum analytically and finding the final result as a function of the energy. And the plot looks like this. So here I plotted the density of states for various supermultiplets of the theory. This is the density of states for the ground state supermultiplet. And that density of states just gives you a delta function. That's very different from the previous result, which had no delta functions in the density of states. So here I see that the density of states actually shows that there's a ground state degeneracy for the BPS black hole. Then I have a density of states for the supermultiplet that includes j equals 0 and j equals 1/2. And actually, this density of states is very, very similar to the one in the non-supersymmetric theory. It's still the sinh of some square root of E, but this time it's the square root of E minus J squared. And very importantly, the density of states contains a theta function, which shows that things are non-zero only when they reach this energy level. And finally, there's also a supermultiplet containing j equals 0, half, and 1 that starts at a slightly different value. And beyond that, there's supermultiplets containing even higher and higher spins. Here, I just plotted the supermultiplets that contain black holes with zero angular momentum. So for instance, if I look at just the zero angular momentum at the pure density of states with zero angular momentum, I see that there is ground state degeneracy. And very important, our calculation shows that the ground state degeneracy is entirely fermionic. And beyond that, there is some density of states that has a gap. And some discontinuity at a different scale where the other supermultiplet, which is this supermultiplet, kicked in. Great. So that literally shows that our spectrum has a gap. And I want to emphasize that because this phi r, this ESL2 scale that I mentioned previously, that doesn't appear anywhere in the superalgebra, in the PSU112 superalgebra. That's a dimensionful parameter. So this is not a consequence of studying the PSU112 superalgebra and imposing that some unitarity constraint or something like that. Rather, this is actually a strong coupling effect that comes from integrating out the Schwarzian and SU2 degrees of freedom. And I just want to mention that exactly the same density of states can be obtained in a different setup, and we'll do this in the upcoming paper. Namely, it can be obtained in supergravity on ADS2 times S free times T4 or times K free. Depending on what preference you have. So this is the low energy supergravity obtained in the D1, D5 system, where Maldacena and Susskind actually studied, approximated what this gap should be between the extremal and near-extremal state. And they found that it should go like 1 over Q1, Q5. And this is actually, if you look at the parameter what phi r is in the D1, D5 system, that is exactly what we find up to a factor of 2. Well, they didn't actually obtain that. This was more a conjecture because they extrapolate some result from the weakly coupled limit to a strong coupling limit. But they say, okay, should we order 1 over Q1, Q5? We actually find the exact numerical prefactor in this computation. Good. So just to summarize, in this talk, we've used integrability of 2D Yang-Mills and of the Schwarzian theory to account for all the 2D massless modes that can possibly occur from a dimensional reduction of near-extremal black holes, either in supergravity or just in Einstein-Maxwell theory. For the case without supersymmetry, we found no gap. Which also suggests that e to the S0 does not count the degeneracy of the extremal state. For the case of supergravity, we've actually found the gap, this gap. We suggest that the extremal state actually counts the degeneracy of, that e to the S0 actually counts the degeneracy of the extremal state, which is exactly something that's predicted by, for instance, Strominger-Vafa, right? And more importantly, it also verifies that many computations that people have done recently related to comparing indices of the black hole to black hole entropies are well motivated because we found that the ground state here is purely bosonic. So if you compute the index of the theory, this state that preserves supersymmetry is accounted for correctly in an index. And I just want to compare this to the no-SUSY case, where indeed, if you naively look at different spins, it might seem that there's a gap. But if you look at j equals 0, for instance, you'll see that there's a continuum of states starting at each j. So starting at each Kerr-Newman black hole. One can essentially say that the near-extremal black hole is equivalent to a specific effective one-dimensional theory. In the case of 4D Einstein-Maxwell, the effective theory that one could study is a Schwarzian coupled to a particle moving on a U1 times SU2 or SO3 manifold with certain couplings and potentials given by the parameters of the black hole. In 4D n equal to supergravity, things are somewhat simpler because we don't have these extra degrees of freedom, but they're somewhat more complicated because the n equal 4 super Schwarzian ends up being extremely complicated. And I just want to finalize, I just want to mention 3 future directions. One is that it will be interesting to account for massless charged particles charged under U1 in this theory and see whether or not the fact that we're studying strongly coupled, the theory at strong coupling affects conclusions related to things like the weak gravity conjecture. The second is that more recently, the JT gravity has been studied in the genus expansion, and it would be interesting to analyze whether or not there are implications for this genus expansion for these black holes. Now, why have I not done this already? The reason why is because at the scale at which this genus expansion becomes important, that scale coincides with the scale at which Kaluza-Klein modes becomes important and many other things become important. So a careful analysis of what, where this genus expansion becomes important is needed. And finally, I think it would be interesting to study scattering in the near horizon region, and that can be achieved by putting Wilson lines in the U1 or SO3 or SU2 gauge theory. This would be like, studying the scattering of either charged or rotating particles that are rotating around the black hole in the near horizon region in a regime where the gravitational interaction becomes strongly coupled. So that's it for today. Thank you very much. If you're interested in these results, you should look out for this paper that should appear in the next couple of weeks.
Cool, thank you. Let's virtually applaud Luca for the talk. We could take questions now for a bit, I think. So if you have a question, feel free to unmute yourself and ask, and then obviously if multiple people unmute at the same time and there's like some congestion, we'll try to deal with things from there. But
I just had hold on, sorry. I just had a kind of quick question. There was a slide near the end where you said j equals 0, j equals 1/2, j equals 1. And what units is
this one?
Yeah.
Well, this is literally the quantized angular momentum of the black hole.
I see. So probably like h bar?
H bar, yeah, h bar units.
Okay. All right, thank you.
Question?
I have a, go ahead.
No, please, after you.
Yeah, so very nice talk, Luca. I have a question. So at some point, when you're actually, you do the reduction and you start solving for the quantum path integral of the Schwarzian, you mentioned that when the temperature is of the order of the gap or this SL2 scale, it is in that regime that you can take the boundary of the ADS2 as fluctuating, but you do it in the ordinary limit in which we take it that is close to the boundary still. My question is, in which we take the fluctuating boundary close to the boundary in some sense.
Yeah, close to, yes.
You take the epsilon, the usual epsilon. So if you were to take the finite cutoff partition function in that case, would you expect that using that you would be able to access lower temperatures, or you expect that in that regime, maybe the Kaluza claim modes have to play a role?
Yeah, that's a very good question. So I expect that there should be no difference. Like in principle, one should obtain the exact same partition function, but the way in which one would obtain it is that one would see that other modes, so maybe let me go to this plot. So I think what you're suggesting is, what if we go closer to the horizon
Yes,
and
exactly.
impose that the proper length of this, so let's call this L1 and L2, and look at L1 much smaller than L2. And what I would say is that, sure, one can do exactly the same thing to obtain the partition function here. In fact, in a recent paper with Joaquin and another postdoc at Stanford, Krutov, we obtained the partition function of JT gravity at finite cutoff. But the thing that would happen here, I believe, is that the fluctuations in the faraway region, in the region in between these two blue lines, would become important and would precisely compensate for the fact that I move my boundary at a finite cutoff towards the left direction. So here we actually checked, those fluctuations do indeed come from the Kaluza climb modes. And we checked that we can neglect them, that we can neglect the contribution of the matter fields from this region, but we didn't check for this intermediate region. So presumably what would happen is that the results shouldn't change, right? This curve, blue curve, was chosen arbitrarily. So if I move it anywhere, it should be the same. And the way in which the results should stay the same is that other modes that are localized in between these two regions should compensate for the fact that I put things at finite cutoff.
Mm-hmm. So in principle, if you were able to account to all this matter that you're talking about, you wouldn't expect to be able to access lower temperature.
No, so I think the next temperature scale that one would want to access is not T order ESL2, but rather T order ESL2 over S0, or T order ESL2 times e to the minus S0. And in that regime, there are all sorts of corrections that become more important. There's the matter, there's the higher topologies, and so on and so forth.
I see. Good. Thank you.
I had a question which might connect to that regime. As you may know, I've been thinking about the higher genus and non-perturbative and higher genus corrections to the non-SUSY and the sort of small amounts of SUSY cases. And there you can actually then go ahead and successfully compute the additional structure that you get from non-perturbative physics corresponding to little bumps on the background of the Schwartzian. And the naive interpretation is that those are sort of showing you the sort of averaged out discrete spectrum that you would expect for the parent quantum black hole. And then in some of those cases, I can compute, and it's perfect you have this slide up, I can compute a non-perturbative contribution to rho at zero energy. And in some limits, I can show that corresponds to essentially the first
excited state.
The first excited state. So it seems like there's a gap there, but now it's, I guess, from your perspective, it's at exponentially smaller temperatures.
That's right. That's right.
So there's no.
It's at energy. So it's at energies that, first of all, they have no connection. That energy scale that I imagine you probably found, which I think is of order e to the minus S0.
Yeah, it is.
I imagine well, it's not that I imagine. It has no connection to the energy scale that was proposed by Preskill and collaborators in the 90s, where they thought that the gap should be.
Yeah.
So I think that's the major difference. I agree that like there should be a gap here. Now the problem with just doing that is that as I mentioned previously, one would have to account for many other things
Exactly.
before trusting that the non-perturbative completion of JT gravity via, let's say, matrix integrals or matrix models would yield the correct gap for an actual Reinster-Nordstrom black hole.
Because you're saying that there's all sorts of Kaluza-Klein states that also turn on, and one needs to see what they do. So it might turn out that it pertains to it, but one has to check.
Yes. What I was thinking more when I was showing this plot is that there are regimes in which not necessarily higher genus, but higher number of boundaries are very important. So for instance, if you look at the late time spectral form factor, in the late time spectral form factor, the fact that you have the connected geometry, the connected geometry starts dominating at sufficiently late times, even though the connected geometry is suppressed by factors of e to the minus s0. So maybe there is a regime in which one could argue that the Kaluza-Klein modes and the potential for the dilaton, indeed do lead to corrections to the connected geometries, but it might still be that the disconnected geometry is the one that dominates in certain regimes, like if we look at sufficiently late times.
Right, and so then that would include any sort of the contribution just of the pure spectrum, not correlators thereof, and so one would then trust.
Right.
I see. Good. Okay, so that's nice. Yeah, I chatted a little bit last week with Joaquin about this, and together with these comments and his, it's really clarifying a lot about how to think about those non-perturbative results. Interesting. The other question I had was whether or not there were any calculations done analogous to what you've just outlined, or maybe you have but haven't published them, corresponding to fewer higher dimensional supersymmetries, which would, for example, tell you about the n=1 Schwarzian.
Yes, so I don't know about the n=1 Schwarzian explicitly, but I know about the n=2 Schwarzian, which is that if you take the same supergravity with the same amount of supersymmetry in 4 dimensions, but this time in ADS instead of flat space. So this is actually the setup that's relevant in holography that could, for instance, make some predictions about the dual CFT. If you take the solution there, I think for the BPS solutions preserve the amount of supersymmetry corresponding to an n=2 super Schwarzian. So in that case, the n=2 super Schwarzian is relevant. And the only case in which the n=4 super Schwarzian is relevant in ADS is this case of ADS free that I discussed in this last slide. But if I look at ADS4 or ADS5, I preserve less supersymmetry. So now the n=2, we know how to compute the spectrum for the n=2 super Schwarzian, and we know how to compute the index and everything. It's just, again, a matter of correctly accounting for all the extra modes, like the Kaluza-Klein modes and the gauge fields and so on and so forth. But we expect to be able to make predictions for black holes in ADS as well. So one thing that is noteworthy is that the n=2 super Schwarzian sometimes also has a gap, just like the n=4 one.
It depends on R charges you turn on or something like that.
It's not dependent on the R charges. It's a bit more subtle than that. Namely, the n=2 super Schwarzian has an anomaly. Depending on what UV, so if you view the n=2 super Schwarzian as the low energy effective theory for some n=2 SYK, the n=2 SYK has a number of fermions that is Q hat. And it depends, whether or not there is a gap depends on the value of Q hat and whether or not you start with a theory that has a parity anomaly.
I see. Interesting.
So I don't know exactly, I don't know yet what this variable Q hat in the n equal to super Schwarzian corresponds to in supergravity.
I see.
But presumably it has to do with, we believe it has to do with the ratio between the U1 charge of some fundamental field in the theory and the U1 charge of the killing spinner that is associated to the supercharge of n equal to.
I see.
This is somewhat explained in the localization paper by Stanford and Whitman.
Yes.
And and we're also gonna have an appendix about the n equal to super Schwarzian and a comparison with the n equal 4 result in our upcoming paper, which clarifies some of the confusions about the n equal to super Schwarzian and its spectrum.
Good. Yeah, I remember talking to Edward about it, and he was sort of saying those results were incomplete, and it sounds like you're essentially now able to complete that story that they started there.
Well, yeah, I'm not sure if it was incomplete because they didn't know it or just because they didn't write it. I also talked to Douglas, and he seemed to know all of the results that I was telling him about n equal to. So
of course. Okay, great. Well, thanks for your answers. That was a great talk, by the way. Really great.
Thank you.
Might there be more questions? Anyone? Ashton, you're the host. I'll let you wrap up.
Okay. Well, I guess once again, let's thank Luca for.
Yeah, thank you as well for the invitation.
Nice
and if any other question comes up, please feel free to email me.
Great. And seriously, we might call you to give that talk on that other.
Okay. Well, sounds good. Thank you very much.
Cool.
Okay. Thanks again.
Yeah,
Bye.
of course. Well, have a good day, guys.
Thanks, you too.
Thank you.
I'm gonna stop the recording. Maybe not. I don't know.
Maybe I'll just stick until everyone leaves, just in case some questions pop up. So
yeah,
feel free to leave.
Luca, are you okay with us posting this the video
yes.
of this talk?
Yeah, of course. Yeah,
okay, great. Yeah, I'll probably just edit out the chit chat at the beginning and put it on our channel on YouTube.
Great.
Yeah, probably in a couple of days it'll be up.
Yeah.
Thanks again.
Of course.
So can I ask you a question about